Hi, I'm Andre, and I'm going to show you how to derive an equation for the distance an object falls, including air resistance. In my last video, I showed you this equation, which is the speed as a function of time an object falls, including air resistance. So what I'll have to do is write a differential equation. Now, speed is dx dt. So the tangent of a function in the hyperbolic case could be written in terms of exponentials. So I have done that here. Notice that I made a substitution. A will equal what's inside the brackets. So the way I'm going to take the integral of this side of the equation is by doing a u substitution. So I get it u prime over u, because I know what the integral of that will be. So u will be set equal to the denominator here, as I did right here. And then so when I take the derivative, what you really get is a change in signs. It becomes minus the two terms instead of plus, and I have to factor out an a. So that's why I have an a in the denominator here, so that I have a u prime over u in the integral. So I take the integral of that, and I have the ln of u, which is the substitution I made in the u substitution. I take the interval is from 0 up to t, and we'll start on 0 up to x. So when I take the integrals of that, the tricky part here is that you'll get 2 cosh at minus ln 1 plus 1. What I mean is a 0 plus e to the 0 is your 1 plus 1. And that's how come you're going to do ln minus ln would be combined into one natural logarithm by log law. And that's what happened to the 2 in your 2 cosh at. And so now we have an equation for x, which is in terms of time for the distance falling, including air resistance. So I could just rearrange that and now solve this equation for t in 2 steps by raising both sides to e, the inverse function of the logarithm, and then just using the inverse function for the cosh to isolate this right here, and then I just multiply across by vt and g to isolate time. And when I do that, I get something that's rather like this. The orange here would be the trajectory where we'd fall in a vacuum, and we begin falling that way until we depart and become a straight line. A straight line on a distance versus time graph is a constant speed, and that constant speed is our terminal velocity, which we found in the last video. So that's how I would derive an equation for the distance of an object falling with respect to time, including air resistance. This is the equation that I speak of, and here's the same equation solved for time. So I would like to do an example problem for you, which I thought would be pretty interesting. Let's take a look at Galileo. And we'll use the acceleration equal to gravity to be just 9.8 meters per second squared. And the atmospheric density, which we will need for the terminal velocity, will be 1.3. And that'll be kilograms per meter cubed. The coefficient of drag will be 0.47. What we'll do is Galileo is up on the Leaning Tower of Pisa and he drops two lead balls. One has a 1-inch diameter sphere, and the other one is larger with a 3-inch diameter sphere. So those are very noticeably different sizes, and the one is indeed 8 times the mass. We'll use this for the density of iron. So what I'm saying is that the 1-inch diameter, you'll solve for the R, and you'll solve for the volume, and you'll find the mass using the volume and the density. And there I found it to be 0.0618. And then the frontal area will be pi r squared, which I found to be 5.07 times 10 to the negative 4. And we will be in meters squared, since I'm doing this whole problem in SI units. Now bear with me there, because what you get is a terminal velocity of 62.5 meters per second for the 1-inch diameter ball. And then if you put all of that into this equation, the time for a 1-inch diameter ball to fall it's 50 meters drop from the Leaning Tower of Pisa is 3.0555 seconds. But the 3-inch diameter ball would fall slightly less time, and the difference is only 0.0370 seconds between the two balls. So that would be a pretty good demonstration for Galileo's students. You know, he could be up there in the Leaning Tower of Pisa. Everyone can see the obvious difference between the two balls. The one's 1 inch, the other's 3. And yet they would fall together and hit the ground only 40 milliseconds apart. I mean, that's virtually the same moment, which is what Galileo is saying. All objects fall at the same rate. Thank you very much for watching my video. I'll be making some more in the future, so please watch my other videos. Continue to take care, and I'll see you again soon. Bye.